let's shift a bit from the brain to another organ, and actually the largest organ of our body. That is approximately 7% of our weight, and that is the skin. And more precisely about the coupling between the skin microcirculation and an external mechanical loading. So why is this interest in the skin? Especially this work was conducted in the context of pressure ulcers. So if we look to cut up skin, you have a stratified tissue with epidermis, dermis that is vascularized, and the hypodermis fat. But when you're in contact with a medical device, let's say a bed at the hospital, a wheelchair, or a prosthetic, the underlying tissue is deformed, and this deformation actually cuts the blood vessels, shuts the blood vessels, and cuts the supply in oxygen. But if you sustain this deformation in time, for instance, for paralyzed persons, they won't sense the fact that the tissue is suffering, then it will lead to the tissue death. And this tissue death is called pressure ulcers. And according to the national panel of the National Pressure Injury Advisory Panel, so we know that there are many factors at the onset of pressure ulcers, but yet we are not at ease to understand how they interplay one to the other. And that makes it a silent epidemic that today still 1 in 5 hospitalized patients in Europe are affected, and worldwide it raises up to 50% rate. And so the current tools are first when engineers, together with the clinician designed medical device, will use pressure mapping to try to relax the positions in which the pressure might be super high and therefore deform much the tissue. Then during the hospitalization, they rely on clinical scoring, and these clinical scorings are superficial assessments by the medical staff of the state of the tissue, and there is a clinical blind spot at this moment because we can't see actually what's happening underneath and this tissue suffocating. And then there is the pressure ulcers that appears, and it's already too late, damage has begun. And therefore, this study aims in trying to study the interplay between the mechanical deformation at the macroscopic scale together with this microcirculation. And so to make so, we just see the skin as a sponge. So we have this stratified structure, just like before, but if we zoom in even more, we have different phases that coexist. The solid scaffold made of collagen and structural cells, some interstitial fluids with mobile cells in the interstitium, and finally the blood and the oxygen. And the idea by seeing it as a sponge is that when you'll squeeze it, the fluid will be forced out of the region being squeezed. Then, if you sustain the load, the fluid can still move internally, and finally, if you release it, the fluid will rushes back in. And so we designed this big compartment porous model with the strong hypothesis that the blood vessels interact primarily with the fluid constituents, meaning that when you have an external load on the structure, first it will increase the force in the solid, then this will be transmitted inside of the pores to the fluid, and finally this will squeeze the blood vessels. But the transformation goes the other way around too. And so we have this bench of equations we use, so mass conservation for each of the phases, solids, cells, oxygen, interstitial fluids, blood, a force equilibrium to a total stress tensor, that is the combination between the solid and fluid tensors, and finally a bench of constitutive laws that all together will allow to make the model closure. And today I'll present you a part of it as a sub-model from this wide model I presented you just before, with only 3 phases, namely the solid, the interstitial fluid, and the blood vessels, because of the experiments I'll show you right after, the timescales and the capacity we had to measure data. And so we have the mixture continuity, the blood continuity equation, and finally the force equilibrium. And the final system, in its weak form, looks like something like that, and thanks to the UFL language, it's quite easy to play with it and have some more internal laws, such as for the vascular permeability or the evolution of the vascular porosity in time. And so we apply it to the mixture continuity, the blood continuity, and the momentum. And the problem I will show you today is about the quarter of a phalanx of the mid finger that was simplified to this mesh with some boundary conditions for the fluid flows in pressure. We imposed a 600 micrometer per second fluid flow for the blood. The internal fluid was able to leak from all the lateral surfaces, so in the direction of the finger. And this force was applied by a laser Doppler probe, I'll come back to it right after, that measured in the red region the laser Doppler flowmetry, meaning some derivation of the measure of the blood velocity. And so we implemented it in FEniCS, so in the version 0.90 by the time, with Taylor-Hood mixed formulation for stability and using a MEMS solver. We played with different meshes, and following mesh convergence, we kept 44K mesh elements that was generated with the Gmesh, benefiting from this direct exchange between Gmesh and FEniCS. And we were able to have a speed up of the computation thanks to the MPI capacity of FEniCS2. And so aside, we carried out an experimental campaign. So this is the finger. There is the laser Doppler probe that was used both to load and measure the outputs. So following an ethical approval, we tested it on 11 human volunteers, controlled the finger indentation, and measured this kind of curves, that is the real-time laser Doppler flowmetry with two loaded phase at the first magnitude, then two other loaded phase at another magnitude, and each time we relax in between and wait a bit. And so these are the typical curves to obtain. So these plateaus are called the ischemic state of the skin, meaning that it's deprived in blood and with a reduced oxygen supply. And these massive spikes are hyperemia. And hyperemia is just like kind of a water hammer impulse inside of the veins. And when we overlay our models with some different sets of material properties, so we carried out a variance-based sensitivity analysis. These are just qualitative results for now, and we are currently working on some patient-specific calibration. We can see that the models actually were able to capture, on one side, the ischemic response with a reduction of the velocity directly beneath the loaded region, and the hyperemic spikes too, that we were quite happy of, with a swelling and an increased velocity also directly under the deformed region. And so far, it was shown in the literature that these hyperemic responses were rooted with some temperature effects, with some neurological aspects, but not much about the mechanics themselves. And all the codes that we developed in this study, aside with the experimental data and also some 1D test cases, are available on these GitHub pages. But you can also find the full theoretical developments inside of this article that was accepted end of last year. So just to conclude briefly, we integrated a big compartment hierarchical porous media framework inside of FEniCS version 0.9, and it has the capacity to handle also some different length scales in time for the cells and the interstitial fluid within the interstitium that I haven't discussed a lot there, but that is already implemented too with the oxygen diffusion inside of our package. And for the model itself, we were super happy, to be fair, of the outcomes we had with just a qualitative assessment for now, with its capacity to have ischemic and hyperemic responses, and it was scalable to HPC simulations. For the boundary conditions, because we're dealing with biomechanics, still we have a lot of tighter experimental control to deal with, to be really conscious of what we're simulating. And we also need to somehow address the literature gap we have on some of the mechanical parameters. For instance, the stiffness of the skin has a range of 1 million between its lowest value and largest value identified in the literature. And finally, for the future work, we should expand the study. That is for now for 11 subjects of age 25 plus or minus 2-year-old to elderly people. So it makes more sense with regard to the pressure ulcers concerns. And I'd like to thank you for your attention, the FNR for its funding, but also some people in the room like Jack that helped me a lot when I was lost at the Unilu, but also Dokken on the discourse that was there to answer. Thank you very much.
are there any questions for our speaker? Jack?
So you have this these pressure ulcers that presumably develop over quite a long time frame. I wondered if you thought about how to kind of couple the time scale on which you do the simulations into a proposal about how the actual thing that you're really interested in might develop.
So that's a really nice point you rose out, and the idea is that so for this experiment I showed I only have one time scale, and that is a short one because of the loading path I followed. But for pressure ulcers, we would need to monitor more on hours-like studies. So it could be a loading phase with a short time stepping. And once the consolidation of the poromechanical model kind of stabilizes in pressure, we could increase the dynamical time step that's quite easy to implement in FEniCS, by the way, to move on the cell's behavior in time and have maybe some contractility further. And right now, the PhD student that's working on the follow-up of my work is implementing some damage and remodeling growth inside of it. So we increases the timelines here. Yeah. So for the sake of being in a 10 minutes time slot wasn't possible to have everything, but say we made almost a Sobol index sensitivity analysis. So I took off some of the parameters of the model, namely the Young modulus. This power alpha is actually an exponent that rules the reduction of the vascular permeability with regards to the amount of blood that is still present in the region. And K is the bulk modulus of the vessel, and assumed to be the bulk modulus of the vessel. And what we saw is that computing first the first order indices, variance-based, so we run something like 70 randomly points taken, and we have this Young modulus, so the scaffold capacity to hold the loads directly that had a role. Because if it's able to sustain the loads, then it's not transmitted that much to the pores. And if the pressure is not augmenting, then the blood vessels are not squeezed and we don't have these ischemic drops. Samely, if this alpha is increased too much, it will have a direct impact inside of the Darcy's law. And so that might change the capacity to have this nonlinear reshape by the end. But what was quite interesting is that when we computed the second order, and this is because we wanted to see also the limitations of the model and especially the couplings that might exist between the parameters. Like you could not calibrate this alpha without taking also the bulk modulus that is inside the variation of the porosity itself. And so yeah, right now we still need to figure out how we could assess it from the experiments, and that's bit of a pity because it's derivative measures for all the variables almost.
So we have some more time for questions. So I have a question. So something that made me very happy was that you didn't talk about any issues with the modeling, and that FEniCS was great. But is there anything that you think is missing in the FEniCS part of the?
So by the time I was missing this submesh that I wasn't able to properly handle, so I could have had bone inside and make a more full region. So I went to this quarter region because I did not succeed to properly deal with the interface between the bone and the tissue itself. Since our discussion of yesterday, I want to try it again and see what's happening. And otherwise, I had a lot of coverage with the memory sector fault, but following Jack's commenter on the comments on the capacity to make these temporary folders, also I need to try a bit, and once I'll try them, probably I'll come back to you with some further remarks. It would be my pleasure.
I'm looking forward to that. So I think we should all thank the speaker again.